Welcome back to today's session. So today is day 2 of the second international conference on energy and AI, and hope you have enjoyed the talks and discussions we had yesterday, which was on AI and energy materials. So today we will continue our journey and we will move on to our second theme, which will be on AI and energy devices. So I'm the chair today, and my name is Huizhi Wang, and I'm from Imperial College London. And we're very honored to have Dhammika, Zhiguo, and Shuang with us as speakers and panelists for today's session. So just the same as yesterday, today we will have 2 invited talks. So today we will have 2 invited talks followed by the panel discussion, and we will be recording today's session, and we will be posting it on our YouTube channel afterwards. So you're welcome to interact with our speakers and panelists during the whole session by posting your questions in the Q&A. So I will be collecting your questions after each talk from the Q&A, and I will try to cover all of your questions, but if I cannot, do apologies. So the first talk will be from Dhammika. So Dhammika is an associate professor at Warwick Manufacturing Group at University of Warwick in the UK, and he completed his PhD in system identification from Warwick, followed by a postdoctoral position at the Free University of Brussels, where he applied the methods to battery modeling. At Warwick, he continues to develop system identification with related machine learning techniques and works closely with several UK industries to transfer the research into applications. So thanks very much, Dhammika, for joining our conference. Now over to you.
Thank you very much, Huizhi. I'll share my screen.
I just stopped sharing my screen.
Sure. Great. Is that visible to everyone?
Yeah.
Okay, fantastic. Right. Good afternoon, good morning, wherever you might be joining from. I would like to start by first thanking Billy and Huizhi for organizing this very relevant conference and for kindly inviting us to present. So yeah, thank you very much. And it's been some really nice talks yesterday. I'm looking forward for the rest of the talks as well. So my name is Dhammika, and I'll be talking about data-driven modeling for lithium-ion batteries with the focus on aging. To begin with, I thought I'll start off by saying, why characterization is important for devices, which is the theme of day number 2. So characterization plays a big part, and the way I've seen it from the research you've done is it's certainly important for early product development, right? And given that in a BEV or battery electric vehicle, the battery pack constitutes more than 50% of the powertrain, it's the most expensive component, it makes a lot of sense why OEMs put a lot of effort to make sure that they choose the right cells and the designs when they build a powertrain for the electric vehicles. So when it comes to characterization, there are quite a few things one might look into, but what it comes down to, at least in the labs and from the models, is what can we measure and what can we do with it. So in the figure in the middle, you see are the typical measurements that we are restricted at the device level. It's not a lot, but this is what we can get access to. It's the current, voltage, or the power, and subsequently the responses that you get from it at some given temperature and perhaps at different state of charge. So ZE is a state of charge. So given these sort of measurements, typically I could think of 3 characterization regimes one might be interested in. The first one is the electrochemical characterization, and this could be in the order of several weeks, with a view of answering certain pack performance, right? So before choosing the right cell, you might want to do this electrochemical characterizations, for example, do capacity tests, the rate capability tests, get the resistances, look at the OCV curves for thermodynamics or level of hysteresis to be able to understand how the pack will perform for that cell. Another important characterization is the thermal behavior of the packs. And this, again, will be looking at things like heat generation, how can it be extracted very quickly, and that's also plays a key part in the pack design, the thermal, the thermal management and the thermal design of an electric vehicle battery pack. And finally, there's another important characterization test, which is considerably longer. It could be in the order of months or certainly several years as well. And that's to understand the warranty risk predictions of the subsequent battery packs. And this is where you would do sort of lab-based tests on cycle life, storage aging, or run custom warranty profiles for the different applications. So for this talk, I'm going to focus quite on this last part of the characterization of aging characterization. I'm going to show you some of the work which is in progress that we've done with some of the data that we've collected in our labs at Warwick. So if you're familiar with battery aging and certainly running long-term aging tests, you might see, you might be familiar with some of these graphs that you're seeing here. So what we're interested in is how the capacity is retained in a particular cell at different conditions. So the graph you're seeing here is an example from our labs where we show the percentage capacity on the vertical axis versus the discharge throughput on the horizontal. And these are done at different temperatures, so at 0 and 10 degrees Celsius, and at different discharge rates, for instance, a normal discharge of 1C, a slow discharge, and what I'm calling a fast discharge for the cell of 2C discharge. So these behaviors look quite good in the sense they appear to be degrading somewhat linearly. But if we start pushing them harder in sort of fast charging, we get some interesting results, or even fast discharging. So if you start doing fast discharge at low temperatures, the linear behavior suddenly changes after a certain discharge throughput, and you get this sudden fall in the capacity. And if you push it even harder with fast charge, so what you're saying is two fast charge scenarios at low temperatures, really the battery doesn't last that long at all, and you get this sort of what's called the knee point effect, or this rollover capacity really kicking in at an early stage. Right? And this is what makes things quite challenging and also interesting from a research point of view, saying, could we try and describe this through models, through mathematical models, so that we can preempt what will happen for the battery at different conditions. Right? And there are different ways people approach, and we'll look at some of the data-driven methods briefly in this talk. But before we go into that, I would like to define 3 problems the way I see it, at least, what people try to do when they talk about modeling battery aging. So problem number 1 here, I'm calling it predicting end of life. And the way I sort of classify this problem comes down to how we define what the validation data set is, so what the characterization data is, or the training data, and what the validation data is. And based on how those are decided, these problems sort of come out quite naturally. So problem number 1 is what I'm calling end of life prediction. And what we try to do there is to say, for a given set of features obtained at an early stage of your battery testing regime, right? So that's shown by this green region here, and that's denoted by this big X. You're interested in saying what the end of life is. So in this case, the end of life is the number of cycles, or the discharge throughput denoted by Q, before it reaches a certain threshold. So you can then start ordering them as pairwise data sets, saying, okay, I've got my training X1, X2, certain number of features, all constrained to the first, let's say 1/3 of your experiment, but you want to subsequently map it to these end of life points Q1, Q2, right? So that's the training data. And then you say, if I get a new operating condition from this region, this green shaded region, can I say what the corresponding end of life is going to be? What the number of cycles it's going to be, or the discharge throughput before the cell ends? So this is one of the problems some people tackle and say, they try to look into data-driven methods. A second problem is, rather than the number of cycles or the end of life per se, you might be interested in the actual capacity fade of the battery. So this is problem number 2. So it's a slightly different in that the training data now gets adapted by, rather than Q, you get the capacity coming in, and they inherently become time-dependent quantities as well. So you say, I've got some training data again at some time interval X of T1, and I've got the corresponding capacity at time T1. And we could also generalize it further and say, I'm also interested in a few more cycles ahead into the future, so T1 plus R. So you could then collect this as pairwise sets of data for your training and say, if that's my training conditions, for example, it could be cycling, calendar, or even previous capacity could go into, populating this X vector or vector quantity or matrix. and you're trying to then say what the capacity is. So given that, you train a model and say what's going to happen at a later stage with a new set of conditions coming in, a new operating condition coming in, what's the subsequent future capacity going to be, right? So we could use such a problem as well to possibly answer what the end of life is, because we could say, well, how long is it going to take before this capacity reaches 80%, right? And then if it answers that question reliably, well, then you have a good estimate on the end of life. And the final problem I would like to address is this much harder problem, whereby we really bring in the dynamics into it and say, rather than features, we're going to look at the signals that's exercised in the battery. So the current and the temperature, for example, these are functions of time. And you have some responses, the voltage and capacity, which is also could be thought of as a function of time, but occurring at a different time scale. Could I find a model with these as my training and subsequently validate on a completely different drive cycle, different temperature, what the voltage response might be, and what the capacity fade might be. I think this is a much harder problem because you really need to get some of the dynamics correctly modeled, I think, for such a method to work. But nonetheless, it's a problem of interest, and I think there's some work being done in this area as well. Right. So with that said, I've sort of organized my talk into 3 parts. I'll talk about the data that we've collected and where some of these problems have been looked into. So in particular, I'll talk about this problem number 1 and problem number 2, rather than the third problem that I spoke about, and show some of the data-driven methods that we've applied there. Mind you, this is still a work in progress. So there's still some results we're hoping to develop, and it's still far from being complete. But you'll see the general direction. And finally, more alluded to problem number 3, some future directions where I think the dynamics are quite important, and how that could be beneficial is something I'll touch upon as well. And conclude the session by bringing some of the points together in my view, what are the key areas that we've experienced from the work that we've done. So start with the data. At Warwick, we've been working with a cell for quite a good few years. It's a 21700 cell by LG. It's a 5 amp hour cell. It's a very relevant cell, and it's a NMC 811, so high nickel on the cathode, and also got a blended anode with silicon and graphite. So it's quite relevant in terms of the chemistry. It's classed as a high energy cell, and we've been doing considerable tests on this since December 2019. So we've tested over 300 cells, and the usual approach with long-term aging is you would conduct what's called calendar aging tests, which is sort of you leave the battery idle at some SOC point. So in our case, we had 13 SOC points and 4 temperature conditions. And you would do certain measurements, what's known as reference performance tests. So to get the capacity and the resistance periodically. And we've got we've got 222 cells running in these conditions. There's still some of these conditions are still ongoing, and we hope to keep them going at least until end of this year or middle of next year. Similarly, we've been doing cycle aging on these cells at different temperatures. So 0, 10, and 25. The 0 and 10 is now complete. 25 started and still ongoing. 45 is in italics because it's about to begin. And we're doing fast charging, slow charging, sort of normal discharge, variable depths of discharge, etc. on these cells. And again, similar to calendar aging, it's undergoing RPT tests to get the capacity and resistance periodically. It's a lot of effort when you're doing these long-term aging cells. If anyone's tried to do them, many things can go wrong. So you need to sort of keep a close eye when these experiments do start, and that's something we've also learned and had to streamline, improve along the way. And got a very sort of data, the CSV and the MAT files. And also the nice thing is that we've if you're from an academic institute, all this data is available. The tests are still ongoing, so do get in touch, and I'll be happy to share it. If you're a PhD student or a postdoc, you can make use of this data if you think it's useful for your work. So yeah, so this is something we would like to make it open, and it's freely available. Okay, so let's look at some of this data a bit more closely, just to give how this background on how this data was collected. We run them in oil baths for the cycling aging. So all the cells are immersed in this sort of tank here that you're seeing here. and it gives us very good thermal management and also safety. So, if one cell fails, there's certainly no thermal propagation or thermal runaway events because of this immersed approach. But for the calendar aging activities, we were using thermal chambers. We had 4 thermal chambers in our labs set at the 4 different temperatures, and the cells, as you might see in this picture, kept at different SOCs, being calendared for over 70 weeks at the moment. Okay, so maybe let's look at some of these data-driven approaches. The first one I would like to briefly touch upon is a transfer learning method that we've looked at. And the way I see it is very much the challenge we've seen in the past is being able to have models that can describe a wide operating condition. I think this is where some of the research challenges lie. You could build data-driven models very well for a given operating condition. It might work fairly well, but really from application point of view, you want these models to then work over a wide temperature condition, different C rates, etc. Right? And that's where some of the issues lie. To address that problem, we looked at transfer learning. And in a nutshell, what you do is you have a neural network and you train this on a certain condition, which we call the base model. Right? So we might train this with certain temperatures, as you'll see later on. And then you transfer some of this knowledge across because you're saying the characteristics are very similar on the new task, on the new operating conditions. But when you're transferring, what you do is you need to remove some of the layers. You retain most of these layers, and that's the transfer learning aspect. And you have to retrain the new layers that you might introduce and the new output. Right? So in this case, we were using current, temperature as our inputs and the capacity as the output measure. So this is problem number 2 that I spoke about earlier in the talk. So we use this transfer learning approach with LSTM as our architecture on the cycling aging datasets that we have. So on the cycling aging, we have 3 temperatures at the moment and 5 C rates. And the C rates that you're seeing here are the charge and discharge rates. So 0.3. So the first number you're seeing here is the charging, and the second number is the corresponding discharge rate. So there's five conditions. And what we did here was we used the first 2 temperatures, or let's say the 0 and the 10 degrees, to train a baseline model. And we've used all the data available to us. So 100% of the data was used for this purpose. And then with that as our base model, so that's this middle pink box that you're seeing here, we subsequently use the 25 degrees data set, but only partial data set of that. So we're saying we use the 30% of it, say, to retrain the model and subsequently predict and validate what will happen for the remaining 70%. Right? So I think the application of this methodology will be, we can do things in the lab quite well-controlled manner. So that might help us get good baseline models. And then once this model gets deployed in a field, could we use some of the on-field data to retrain it and validate the subsequent? So that's sort of the direction we would like to head to and evaluate how this might behave. Okay, so here's some of the results from the baseline model. So this is still the training phase at 0 and 10 degrees. So there are 10 conditions from this table. I'm only showing 4 of these conditions here. And what you're seeing here are the fast charging conditions. This is the 0.5 C charging at 0 degrees, and then 0.7 at 0 degrees and 0.5 at 10 degrees at 0.710. So 4 of the conditions to evaluate how this LSTM model will behave as a baseline model to capture the different C rates and the different temperatures. And it was promising. It managed to capture this capacity fairly well with 98% accuracy. Just a point to make on this capacity that you're seeing here are not from the RPTs. These are not the reference performance test capacity. These are the capacities that we get during the cycling itself. So we were focusing on the actual energy or the capacity we were extracting while the cycling was happening. Right. Okay, once that was done, we then applied this transfer learning method on the 25 degrees case and want to evaluate the performance based on the training the model based on 30% of the data from 25 degrees. So the red region that you're seeing here is the 30% of the data. And again, I'm only showing 2 conditions for the 25 degrees. So the first graph you're seeing at the top is a slow charge and a very, very mild discharge, 0.3C charge, 1C discharge. And the cell is, at the moment, the experiment is still ongoing. It's still sort of a linear behavior. So the model, the transfer learning model did fairly well there, right? It wasn't a very difficult case. But when we looked at the 0.7C, the fast charging scenario, the data already displays a nonlinear sort of starting decay behavior. And the transfer learning model quite encouragingly demonstrated that it can capture this behavior of this nonlinear behavior from the transfer learning approach. And the way we verified this is say, well, what if we didn't do any transfer learning and we just stuck to the 30% of the data to train our model? What you're seeing here is that, with about 80% accuracy compared to 96, you're unable to get any sort of nonlinear effects through this method without any transfer learning. And that, I would say, is not surprising, because what you provide the model, the training doesn't have any form of nonlinear behavior. So why would the model have that description, right? And whereas with the transfer learning approach, you can embed that if you had the data set, which we did in the 0 and the 10 degrees case, right? So we had those sort of features in the baseline model, which is how this improvement comes about. So this is quite encouraging. So that's based on LSTM methods. I would now like to focus on a different machine learning approach, which is Gaussian processes. I think it's a fantastic regression tool. It gives you the statistics you could infer from the posterior distribution, and its GPs are, I think, a great tool, and we're going to see more and more of this appearing in battery modeling is my personal view. And the second method is motivated from this Severson paper with some really nice results they've done in the Nature Energy 2019. And what was quite nice in their work is that they demonstrated this linear relationship between end of life, so the number of cycles to 80, I think it was 80%, with relation to this capacity voltage function. I'll talk a bit more about this. And this encourages us to think, well, how will this generalize quite broadly and onto other data sets as well? So I think they tried different fast charge scenarios at 30 degrees, but we would like to try different charging and discharging at different temperatures and sort of see whether this can be extended to this wide condition. Before I get to that point, this delta Q curve that they've introduced is a capacity estimate, is a difference in capacities, and the way it's defined is you have two cycles. So the ith cycle is blue here, and the jth cycle is red. You need to look at the discharge voltage curves, the voltage versus capacity plotted, and you compute the area under the curves, right? So there's the extra capacity, and the time limits are defined as the time it takes for the battery to go from Vmax to Vmin, whatever Vmin might be for the corresponding cell, right? So this needs, to get these features, the battery needs to be discharged fully so that you can compute these functions. And once you do get it, it'll look something like this. It's not a very it's not a very common function that we might be familiar with, compared to EIS, for example. But nonetheless, it's got this very interesting feature once you do calculate it. And in their work, they've looked at the variance of this entire characteristic and demonstrated that there's a linear relationship between that and the end of life. But over here, we were interested in trying to model this curve before taking any variance, and we looked into Gaussian processes as an option. So this is the work that's still in progress. We've got a few more steps to go, but what's encouraging at the moment is that we are able to explain that behavior, this delta Q curve, at different temperatures. So what you're seeing here are the three different temperatures of this delta Q curve. So the top curve is at 0 degrees, the middle line is at 25, and the bottom line is at 0 degrees, 10, and 25 degrees Celsius. And each column are the different C rates. So the way it works is we have one Gaussian processes model describing the different C rate per temperature, but then we need different Gaussian process models per temperature. So what this is telling is that we can describe the C rates fairly well, but there's a distinct difference in the kernel functions when it goes to the different temperatures, right? So you can't use the same kernel to explain the different temperature behaviors, and of course we tried that method and it starts to fail, but we had to sort of separate them out. Right? So as we go along, the next step for us in that direction is to learn this temperature dependence of this delta Q curve, and Gaussian process regression networks is where we're looking into, and hopefully in a few months' time could say a bit more about this, or be able to write about it. But this is the key challenge we're trying to get to, and like I said, it's being able to get these data-driven models working on a wide operating condition is I think where some of the research challenges lie. And once that works, we then finally to map it to end-of-life estimation. So this is problem number one in out of those three problems I spoke about, to see whether you could map it to some end-of-life definition, maybe it's 80%. But the nice thing is with these Gaussian process regression networks, you could do multiple outputs as well. So you could also include capacity as well, rather than just the end-of-life cycle numbers. Okay, so with that said, I would sort of like to gradually bring the session to an end by looking at some future directions. And this is some work we've done called multitask latent forces. But before that, maybe let's see why it might be necessary. In my view, I think data-driven approaches are great in the sense you can quantify the uncertainties, right? So you can get sample means, sample variances. Really, the data is going to tell you what the uncertainties are. And that's where a lot of the value is in that. But it's certainly, at least the methodologies we are following, including the ones I've shown today, these are fairly, and it doesn't account for dynamics explicitly, right? Whereas physical models, they do account for dynamics because that's how you start off writing the equations. And the value there is then you could account for things like path dependencies, right? So if you have relaxations coming in with cycling and calendar aging, right? And that relaxation interval plays a part in how your capacity fades. We need to think about physical models to have any hope of describing such effects. So it makes sense to then try and combine this, so to be able to bring in this uncertainties from data and the dynamics from physical models. And there are several ways, and there are many ways one might choose to do this. And an example that I'm showing here is called latent force models. So this is some work we've been doing with the Alan Turing Institute, and it's still a long way to go before we can get it working with aging, but it seems to work fairly well with electrochemical models in the absence of aging at the moment. And the idea is this: what you say is we have a grasp, we have a fairly good understanding of the dynamics that's shown by the green box here, and that could have some mathematical representation, for example, state space models, and a ready sort of model as well. And you bring in unknown dynamics, unknown behaviors through Gaussian processes, what's called latent forces. So and then the challenge is finding the dependence of the Gaussian processes on the dynamics is not a very straightforward task, and that's where the training and the decisions have to be made. How do you go about finding these latent forces such that you can sufficiently describe the missing dynamics from the observations that you have? Right. So I think this is, again, Gaussian processes have that flexibility, and like I said, it's a great tool, and they can be appended to dynamics to enrich your dynamical models. And the nice thing is once this works, you can infer from the posterior distribution some of the state variables and get the true confidence intervals of these estimates. All right. So with that, I'd like to conclude and summarize this talk. I think conducting long-term aging requires a lot of effort. For any data-driven method, this is crucial. You having this data set is important, but at the same time, it is quite an arduous task. And you need to make sure you streamline the analysis and keep a close eye during these experiments, because things can go wrong and you need to somehow rectify them as you go along, right? Because you're putting a lot of effort. You don't want, at the end of the 2 years, the data to be not very useful. So in the same vein, then if a lot of effort goes in, I think that it has to be accessible to other researchers, right? It only makes sense to make it open and beneficial for other use as well, if the data is of use. And with some of the techniques I've spoken about, transfer learning, I think, has the potential to model a wide range of operating conditions. And this is based on some of the conversations we're having with OEMs, where they're requesting models that are robust, covers a large DOD, currents, temperatures, and therefore you want methods to cover that large space is where the emphasis is what we've seen. And when we move on to more physical models, I think something that's not done quite thoroughly, in my view, is validating these models. People get very attached to the models they develop, and they'll be afraid not to probe it too heavily in case it breaks down. But I think that's where we should really push it hard and see at which points will they fail and what's this validating boundary, right? So I think it's quite important to make sure the models are pushed and you find out under which conditions they work very well and under which conditions they don't, because these physical models will sort of be the core modeling framework around which some of the data-driven methods will then be built upon, right? And that's where I think the robustness will lie in these hybrid models. Right, that's all for my talk. So with that, I would like to conclude and certainly pass my acknowledgement. So the transfer learning work was done by Anirudh Gupta at Warwick, so he's done this nice work. And the Gaussian Processes work was done with the work of Alan Turing Institute. James Walsh really helped there. And I would also like to extend thanks to quite a few other colleagues at Warwick and at University of Birmingham, where we work quite closely to get the data sets. There are some references as well on some of this work we've done on this latent source multitask model, pure physical-based models for agent prediction, and sort of purely data-driven models as well is the last paper. So I thought I'll include some of that for your interests. Thank you very much. That's all I have to say.
Very much, Dhammika, for the fantastic talk, and which has shown us actually data-driven model can be a very useful tool for studying battery aging. Thank you very much for the great talk. So, and we know the data collection for model training can always be the challenge. So there are actually questions from our audience. So who asked, in general, how many batteries do you think are needed to be representative of lifetime performance, given that there are natural cell-to-cell variation in manufacturing?
Yeah, absolutely. That's a very relevant question. So, I mean, the simple answer is the more the better, right? Of course, the challenge is the number of channels you have and some practical difficulties. But even then, so we've seen so we're using 4 cells per condition, and over time the variation gets larger and larger. And I think there's some work being done recently from Oxford and a few others where they showed about 10 cells is probably the right number to, at least is a good number of cells to begin with. But the challenge there is then you need to probably focus on the conditions. If you have a lot of operating conditions to cover with 10, with a large number of cells, the number of channels will run out very quickly. So it is a compromise, and yeah, it's a difficult decision to make. So if you want to cover a large space, you won't have the luxury of using many cells. But it's also quite important from the statistical point of view.
Yeah, agree. And there is another question about the transfer learning approach. So how well would using a model to do the initial training be, or are models still too far from the reality or too difficult to parameterize?
I think the way I see it is, the models are fine because some of these techniques are derived from machine learning and they've used it in imaging, for example. These transfer learning ideas have been used in imaging. The way I see it is making the data relevant for the application. So even the data I presented is somewhat idealistic. These are constant current, charge, discharge scenarios. Calendar aging is separate. And I think that's where really what we should start looking into more closely, making these data sets more realistic, dynamic profiles with calendar aging interleaved, and then trying some of these techniques on top of it as well. I think that's where really the value will start coming out then. Right? But what we're trying to show is that at least from the lab data that we're collecting, there's promise, there's potential for these techniques to work. And certainly at our end, in our labs, that's the next thing we're hoping to do, try to generate some more realistic lab-based data sets and then, apply these methods on them afterwards.
Yeah, thank you very much. Thanks again, Dhammika, for the great talk.
Thank you.
So our next speaker is Professor Zhiguo Qu, Zhiguo is a professor of energy and power engineering at Xi'an Jiaotong University in China. He obtained his PhD degree in engineering thermal physics from Xi'an Jiaotong University in 2005. He worked as a visiting scholar at Advanced Heat Transfer LLC in US and Pennsylvania State University in 2006 and 2013, respectively. His main research interests include multi-scale transport phenomena, energy conversion and storage, micro-nanofluidics, and hydrogen fuel cell technologies. He has published around 200 papers in peer-reviewed journals. These papers are cited by more than 4,600 times from Google Scholar with an H-index of 41. He serves as an editorial board member for several journals, including our Energy and AI. So Zhiguo is a recipient of China National Funds for Distinguished Young Scholars, which is very prestigious award in China. So let's welcome Zhiguo Qu. So I will hand over the screen to you, Zhiguo.
Okay, thank you very much for Zhiguo's kind introductions. Can you hear me and to see my screen? Okay, I think you can see. Should I start?
Yeah, come to your screen.
Okay, so to improve the quality, so I turned off my screen. Yeah. Good evening, everybody. My name is Zhiguo Qu from Xi'an Jiaotong University. Today, it's my great honor to be here to share on our work. The title of my presentation is Prediction and Control of Heat and Mass Transfer in Porous Medium using a Deep Learning Method. This is the contents of my presentations. Background, so first is the background. So porous medium, which is defined as a multi-element medium containing a solid framework and a large number of connected pores, such as in the GDL, in the fuel cells tank, in silicon carbon dioxide, or some adsorbent particle bed, compact bed, in a solvent bed, or such as the capillary force of a heat pipe. So they have some great advantage of lightweight, high specific surface area, and high conductivities. So have great applications in the field of hydrogen energy aircraft, such as this hydrogen storage tank, also for thermal protection system or life support system on aircraft. And the loop heat pipe can be used to the heat regulations of the waste heat of the electro components on the satellites. So we want to know the structure transport performance in this kind of porous medium is very important, but and it needs to be further elucidations. And now previous research have great progress have been achieved, but still some limitations. The limits is optimum design applications in some cases, especially in the applications where the volume is highly restricted. So because the porous medium structures have some very conflict structures, such as diverse structures, such as like this way, it's a microscopic molecular structures, and this is for adsorbed particles, and this is kind of metallic foam. So therefore, the structure's performance relations of porous medium and its performance directly regulations need to be explained clearly. So of course, we can use experimental study or numerical study, but you know, the porous structure is very complicated, so it's a time-consuming process. So, so the data-driven method provide a very good tool to do this. So there's still some scientific questions. For example, we want to know the structure performance relationship of porous medium and its performance direction regulations So we use data-driven structure performance to predict and optimize the performance or structures of the porous medium to solve this problem. So we establish the constitutive based on existing structure database and optimum porous structures performance based on the data-driven method. So that's the second part, sample structures information for self-amplification. So as we know, this is a typical gas adsorption bed. And in this bed, spheres compact in this bed. The gas goes in this way and it goes out. So if this happens, a pure gas diffusion process happens inside this area. If we look inside these porous structures, this is the porous structures. So we have some numerical method to reconstruct these constructions, and this is the physical models for simulations. This is the concentration inlet and outlet. And this is the governing equations. And we use this method. Of course, we can use lattice-Boltzmann method simulations based on the Post-School method. We can clearly get the concentrations and get the effective diffusivity. And so effective diffusivity is very important for the engineering design. However, we know for this structure is very complicated. If done the case based on the reconstructed porous structures, is always very time-consuming process. So if we use data-driven method, we need a lot of training samples in the training process. But in some cases, we only have very limited number of training samples. So how did we can get one sample to get a lot of samples or to reduce the samples? So we propose a self-amplification method. For example, this is a porous structures. As we know, for this kind of porous structures, it has a characteristic of self-similarity from its structures. So we have an idea, we can cut off this porous structures, cut into very small pieces, and we assume that the very small pieces, the element, so its performance is similar to the whole three-dimensional porous structure. So based on this idea, we can get for this one, we can get 100. Then this one is 200 LU cubic. Please, you can cut it into small pieces, and each piece is the size is 100 LU cubic. So together we can get a lot of subdomain, and we can, of course, we can easily to restrict. We can easily to extract the mass flow flux and the structure informations to get more samples. Based on this idea, we can, for example, we can use one sample with size of 200 cubic. It can be decomposed into 4,000 subdomain samples with a size like this way. So the number of samples was greatly improved. So this is our Xi'an models. We based on this, we set up a three-dimensional convolutional neural networks. This is the Xi'an prediction models. This model have typically input layer for, we can input data for convolutional layer. We get a feature, extract the features maps, and for the pooling layer to get the maximum of the features and the dropout and the output. And after each kind of iterations, we get the diffusivity. So this is the whole process for our models. Now let's see the results. This is the diffusivity for this packed bed. And we found that we interesting found that, and this diffusivity increase with porosity. That is, we can easily understand, because if the porosity increased, the volume increased, so that its gas diffusivity is increased. But however, we compared with 4 results, 2 empirical correlations named Weisberg equations and the Bergman's equations, this one, and the results by field simulations with lattice Boltzmann equations, this method is this one, and this was predicted by CNN. We found that our predicted by CNN is more close with lattice Boltzmann method, and the two empirical correlations is a little far from the results. Why this happens? Because, as we know, these 2 classical equations is based on the macro assumptions. So it's a macro scale. So it's a lot of empirical parameters. But in our CNN method, so the training samples is based on the pore scale structures. So it's this pore structures is very similar to the real structures from the physical essence. So this can explain why the CNN results is more close to the LBM method. Let's say the computation time. We found that this is the CNN training per case, and this is, and we use GPU hours. Even we will use NVIDIA GeForce in this time this way. And but for the CNN, we use CNN prediction time per case. This is the time 3 to 10 minus 4 hours, and the LBM simulations time per case, this is about 16 hours. So the time is greatly reduced based on this method. Then let's see the next part for the transport with varied structures and various structures and the boundaries. Why we want to do this? Because we have 2 parts. Sorry, the first part is transport properties with various structures. You know, as we can see that different structures have very complex structures. So if
Professor Chu, we cannot hear you.
and heat transfer conclusions, if a gas diffuse in these particles and if some chemical reactions such as adsorption happens, so only adsorption heat can transfer inside the packed bed. So these are governing equations and boundary conditions. So this is a typical structures, and we use these structures as training process, packed bed. However, if we want to know the performance of other structures, such as like this one, irregular porous, also fibrous porous, with curvature, its ligand is always straight or can be a curvature fibrous or some gyroid structures or like foam structures. So if we only use one structures as training samples to deep learning model sections and continue to deep learning model learning, we can use these structures to predict the performance of the other structure. It should be very interesting. Of course, we find we can do this. We can use this method. We can get, even we can predict the concentration field. That is, let's say, we can not only predict the general transport performance such as diffusivity, we only can predict the concentration field corresponding to effective diffusivity. We also can predict velocity field corresponding to permeability, and also we can get the temperature field, we can get the corresponding effective thermal conductivity. Now, at first, we should validate our models, and we get a reference from the Journal of Fluid Mechanics. So this is the experimental studies, and this is a velocity inlet in the packed and packed spheres, and this is the experiment data from the experiment data from the LPV LISA photography. So, and this is, we get the results from the CNN model data, and we found it's very similar. And also this gets the velocity profile and some locations X, Y is given specific locations, and we can get the and the results are predicted by the velocity predicted by our results and models, and predicted by CNN and experimental data by the experimental results. So with this classical data, our method is verified. Now let's say, so this use packed sphere. This is, we predict structures, and we can get it, if we get the results, get a concentration field, we can get the training structures. And this is the results calculated by the Lattice-Boltzmann method. This is, we can get a concentration field, velocity field, and the predicted temperature field. And this is predicted by CNN results. And this CNN results will become the training samples for predict other structures. And use this one, we can use packed sphere structures to data-driven to predict irregular porous structures. For example, this is, we get the concentration field, velocity field, and temperature field. And this is the results predicted by the 3D numerical simulations with LBO method. But this is the CNN predicted results with packed sphere. So this is predicted by with irregular porous mediums and get the numerical results. And this is CNN predicted results with the training sample packed sphere. And also we can learn from, based on the packed sphere, this results, we can predict the performance of fiber porous structures. And we found that this is the concentrations, velocity field, and temperature field predicted by the LB method based on the real fibrous porous structures. And this is predicted by CNN results based on the packed sphere. So this is, we can get the field. How about the effective diffusivity? We found this one. This figure shows that, you find that this is a predicted diffusivity predicted by the CNN, and this is predicted by the Lattice-Boltzmann method. And this is two equations from the empirical correlations for these irregular structures. And this is for, to predict the fibrous structures. So, and also we can use these structures, packed sphere structure, to predict the irregulars or the permeability coefficient of irregular porous medium and the permeability coefficients of fibrous porous medium. So this is permeability, this is diffusivity. So the two very important transport coefficients, effective diffusivities and permeability, can be predicted by the training samples based on the very simple these structures. Also, we can get more complex structures for J-road structures. We also get similar results. So let's see the comprehensive performance for the J-road structures. And this is the LBM results from numerical field simulations. And this is the values, this is predicted by CNN values. Also, we can, I think, of course, there has some deviations, but these deviations can be accepted by the front point of the engineering. This is the results, the timer results. If you get a three-dimensional field simulations, we need 316 hours, maybe half a month, we can get a case. If we use GPU parallel computing, we can get these results. But if we use CPU hours, use CNN predict per case, so the time is greatly reduced to 1.1 second. Now let's see the second part. We use transport properties with varied inlet temperatures. So we can, even we can training get the different structures, we also get different temperatures. For example, this is a physical model for heat transport for the a gas go this way and was heated or cooled by this sphere bed. So we can get different inlet temperatures. So we use these inlet temperatures. For example, 15 degrees and training data, and we can get the temperature field of other inlet temperatures, such as 100 and 125, etc. And this is T out for the outlet temperatures. So let's find the results. So this is the input data. Use these structures. The training process, like in this way, use sphere packed bed and deep learning model sections, and we can get different predicted results. Different delta T means different temperature difference between inlet and the outlet. And if this one training sample, the temperature delta T is 25 degrees C, and this is the training samples, and we can get the delta T to 75%, and the delta T is 175 degrees. So we based on this way, we can get the effective thermal conductivity. This is the temperature field from the field simulations, and this is predicted results by the CNN method. So we can get one inlet temperatures can get the results of other temperatures, include the temperature field and effective conductivity. And this is for the for another temperature difference, like this way. So the result is similar. So we have a so what about the effective thermal conductivity? This line shows the effective thermal conductivity. We can predict by different CNN with this one. This is the training samples. We can get these lines, and this is, agree well with calculated by the simulations with lattice Boltzmann method. So the feasibility of the method is verified. So the last part, we show some results for directional heat transfer component structures. For example, here is a heat source we can consider as electrical components. This is a porous matrix, such as carbon matrix, and the heat flux go this way. And we know inside this, and we know inside this fibers, its diameters or its fibers structures can be regulated. And what we want to do is try to reduce or cool this electrical component effectively to reduce its surface temperature. So we need to design these porous structures to regulate the heat flow. And this is so we also use this deep learning method, and this is the flow chart, and we use genetic algorithm combined with CNN model. Why we want to combine with genetic algorithm? Because genetic algorithm is a kind of optimizations. So one side we want to reduce time with CNN method. Another, we get if we have a similar target, we can get what we want. Also, we use this way. This is a CNN models of flow chart. This is the initial structures. This is a very which this is the fibers get high thickness or high thickness inside this way. We can design its structures, and we can get initial structures, and we can design the structure to get a composite materials. And this is the temperature in the initial structures and the temperature field in the optimized structures. So based on this way, we can design its fibers, high conductivity fibers assemblies. So we can get optimized structures, heat mechanisms. So this is for the pure carbons temperature, surface temperature like this way. And also we can, these initial structures, and also we can design and optimize structures with enhanced high conductivities. We can reduce the surface temperature greatly. So what are the time consumptions comparisons between GA, a traditional optimization method, and the coupled GA genetic algorithm is seen together, CNN model together? If the data set for CNN coupled is like this way, and the training CNN model is 10 hours, and you say, if we use LBM simulation time in GA, time is like this way. So totally, the time is greatly reduced for these very complicated heat regulations. Now this is a small conclusions of my talk. So we propose a sample self-gain method or sample amplification method is proposed to realize rapid predictions of transfer performance of porous structures with very limited training samples. Second, a three-dimensional, fully convolutional neural predicting. We can predicting the diffusions, flow, and temperature field, and the corresponding coefficients in several typical porous medium is proposed. The third, the CNN achieves in relatively accurate and fast predictions of temperature field and effective thermal conductivities with different inlet temperatures. And in the future, we also extend the inlet temperature to other more complicated boundary conditions. The last one, we can get distributions of high thermal conductivity carbon fiber bundles, insert high thermal conductivity bundles and pore structures to achieve a better heat transfer performance and is optimized. And this work is supported by the National Natural Science Foundation of China. Thank you for your attention.
Thank you very much, Professor Chu, for the great talk. So we've got several questions from audience. So for your, so the first question is, in general, how small can you make a subdomain but still make it representative of the bulk performance?
Okay, so how small is depends on the initial structures of my my three-dimensional porous structure. If the structure is millimeters, or the millimeters, if we want to get the ratio from 1 to 4,000, so 1 to 4,000, if we get more samples, so the size will be reduced. It was divided by 4,000. Of course, if we divide it more and more fine, and the smaller size, the samples will get more smaller, but its accuracy may be reduced. So we need a trade-off ideas. Yeah. So the initial porous structures is about millimeter. Yeah, a few 10 millimeter or 10 millimeter or 1 or 2 millimeters. Yeah, depends on the real background and the real problems, and depends on what want you get from 1 to 4,000 or 1 to 10,000. Depends on the demand. Okay.
Yeah. So there is another question. So how well would your approach scale when introducing multi-physics, such as multi-phase flow?
Okay, this is a great challenge. So yeah, for this yesterday and today we can find that in the journals get the publish some papers for some problems for some such as battery aging is very important case. And for the multi-phase, I think it's more challenging because in the multi-phase we have a two-phase interface, and this interface is always unsteady and will change with time. So it's numerical model because even with multi-phase problems, we also need to do some training samples. But for the training samples, the accurate training samples is always depends on the multi-phase model. I think if the training samples, if the training samples is good enough or its accuracy can be guaranteed, so our CNN model just a data-driven method, and so we can get good results. So it depends on the accuracy of the training samples, or depends on the multi-phase physical essence model, depend on the physical model. Yes.
Okay, thank you very much, Professor Chu. May I please invite Professor Chu, Dhammika, and Shuang join back to our panel discussion session. So for our panel discussion, in addition to our two speakers, we are also excited to have Zhai from Shanghai REFIRE Technology with us. So before we start the panel discussion, let me just give a quick introduction of Shuang. So Shuang is a Chief Professional Engineer of Shanghai REFIRE Technology, and he's responsible for fuel cell system technology development. He has been working on fuel cell system development for 13 years and has extensive experience in the field of fuel cell system in fuel cell technology and product development, especially in fuel cell system stack simulation, system architecture design, freeze-start, and durability. And he led the team in REFIRE Technology to develop 7 series fuel cell system products, which is the product with the most sales and the longest mileage in Chinese market, which is really amazing. And now he and his team focus on the new product, Prisma series development. Before joining REFIRE, Shuang spent 4 years at SAC Motor Corporation Limited as a system engineer and responsible for system simulation and freeze start as well. He is the first person who led the team realizing the fuel cell system freeze start from -20 degrees C. Shuang has a multidisciplinary background in both computational mathematics and fuel cells. He was a winner of the excellent doctoral thesis of Tongji University in China. So you will be able to find Shuang's talk in our conference YouTube channel, where he kindly introduced the efforts in Shanghai REFIRE on the development of fuel cell systems and their associated big data platform, and provided insights into how they use a big data platform for fault diagnosis and early warning, as well as a fuel economy improvement of their product. So you're strongly recommended to visit our YouTube channel, where you can find Shuang's talk as well as many other amazing talks there. So thanks very much for joining us, Shuang.
Hi, everyone. Thank you, Zhiguo.
Our panel discussion will be dynamic and more interactive. I'm collecting questions from audience in the Q&A. Right, so let me start with the first question then. So because we know Dhammika, you work a lot with industry, and Zhiguo, you also have lots of experience in research collaboration with industry partners. And Shuang, you from industry, well, you have worked in universities before. So from your experience and opinion, so what will be the main barriers to transfer AI research in universities to industry, to real applications? maybe we just start from Zhiguo and Dhammika and Shuang.
Okay, thank you, Zhihui. So this is very good starting question. Yeah. So yes, so a data-driven method is very effective. Yeah, it's very effective and time-saving. But I think so. If we want to use this method to connect with industry, so there's a bottleneck or the challenge is that, you know, the different chemical, different engineering process, there are different industry background. So if I was I was heat transfer man, I do some research for such as heat transfer, heat exchangers. I know the physical process inside this in this machine or this equipment. But for other more physical processes, I know the data-driven method, but I have no background of physical process of how the how the regions or how the things works. So if we want to use this data-driven method to industry, we need to know what happens inside the applications equipment. So physical essence is the most important. So we need to get more exchange communications with the persons from industry to know how they work, and will help us to build this data-driven method. Okay.
Yeah, absolutely. Maybe I could also contribute something to that question. Indeed, from our experience, what I've seen is that industry certainly has the ambition, and they've also got the funding behind them to apply some of these techniques. And that's fantastic, because the motivation, the drive is there, which is where when they approach to universities to engage with the research that's been happening at a university academic level. What I've seen is that, from my experience, it might not be the obvious places where things, you know, where the challenges are. So it's not necessarily the hardware infrastructure, the data sometimes. It's often that I've seen is some of the knowledge transfers. So some of this research is very niche, very abstract, and it's not obvious how they could be translated across. Especially like Professor Shu mentioned, the physical domain, you need a bit more specialism in a certain area, and that might be missing in industry. So being able to provide the right training is where I've sometimes seen really the maximum effort goes into. So if you could, you know, sharing the papers is fine, sharing the code is also helps, it goes a certain way, but to really understand something more in depth needs a broader training sort of appreciation to translate the academic problems into industry. And in our case, so we are working with several partners where they have the knowledge on the data side, the infrastructure, they can throw a lot of computation power behind it. But some of the details of the battery models, the physical models, the mathematical equations, and that's missing in some industrial partners. So while we can help and explain that, there's a training required as well before it could be actually used. And I think that there's a challenge where I'm seeing some of the skills and training, so that the niche research that universities are doing can be more effectively translated across and transferred across.
So Shuang, any thoughts from you?
Yes, thank you. Because as you introduced, my background is, I think this question is more from a student. Maybe he's boring for this simulation or others, but I can share my experience. I'm also, you know, my background is to do some simulation and math calculation. And doing like at university. When at the university, I also have this kind of question. I found there's a gap between my learning and the engineer. But when I have a chance to go to the SIC, especially when I join REFIRE, when along with our product development and the problem solving, we found the fundamental is the most important. All the technical problem when we do the deep thinking is fundamental. So I want to share that. So that's why I can lead the team as the chief engineer in REFIRE, because we know all the engineer problem when I transfer that is a fundamental. So I think all we learning at the university when you join the company, you will find it's very useful, especially for the fundamental parts. And that's first thing I want to comment. Another thing is that as the REFIRE example, I think other company also have this. We have the joint library with the university. For example, in REFIRE, we have the joint library with Tongji University and Shanghai Jiaotong University, like that. I think that's a platform for the university student to know how the engineer works. There's some deep cooperation with the university, and we also open some positions as the for the different background students can work part-time work at our company. I think this is also another chance for you to watch how we do the inner work, and you know how you put your knowledge into the real engineer. For example, like what we talk about today, like the big data and the AI technology. I think in my presentation, you can see we have this platform. I think I found another people also ask me this question. I think I can reply to that later. I mean, we have this chance for students to learn, and we can do it together.
Yeah, thank you very much. So as Dr. Zhai mentioned, there is a question specific to Dr. Zhai. So we have heard a lot about how important data is for training model, and often industry have lots of this. So how do we balance sharing data and the need to protect its commercial value?
Yes, in the past we have this. To be honest, for example, we could have running 30 million kilometers in the last season. I think this data value is if it's not development, it's no value. So we want to cooperate with different company. But yes, we cannot totally open it. But if our querying is very specific, we just need some specific part of the data. I think we have the chance to make it valuable. That's the commercial value. Commercial value, if we totally open it, I think because this data hit our different companies' control strategy, like a control strategy, like others. That's cannot be totally opened. But if, for example, you just want to look the data to predict the battery life or the fuel cell life, we just need some of the signals. I think we don't need too much concern about their core strategy and their core value. I think that's possibility. We have that possibility for that.
Thank you very much. And here is a question to all panel members. So I see lots of work where AI is used to speed up existing multi-physics models, but what do the panel think are the frontiers for using AI to give us new physical insights? So maybe we start from Professor Chu again, and Dhammika and Shuang.
Okay, so yeah, so this for the engineering applications, we always meet a lot of multi-physics problems. So if we can get this deep learning method or that kind of data-driven method, we can, because traditionally we can to predict one general performance, such as heat transfer coefficient and thermal effect diffusion coefficients. And now we can predict field study. We can predict concentration field, temperature field. If we get some multi-scale method, if our training models include some other field, such as electric field, because in batteries, fuel cells, we also get some electrochemical equations. So you use data-driven method, we can predict the multi-physical problems to extend its application range. And based on this application method, we can predict its different fields, such as electrical field, current applications in the manual field, or the membranes of the fuel cells. If we can get enough good data or field test data, we can use as training samples. We can predict these multi-physical problems. We can get a lot of field informations in addition to the gained data. So with this quite good field analysis, we found some new happens and new physicals and help us to improve the quality of the products. Okay.
From my side, I probably could share a few of my thoughts. So the research I'm working on is fairly at a, let's say, larger length scale, and the application of AI and let's say more machine learning, to be a bit more precise, is to quantify uncertainties, and its approach as it's sort of more of a regression type tool. So I would be careful to read much into it in terms of physical insight, right? You should have an understanding of how these tools are used for what purpose, and whether you could interpret these techniques beyond that. And I think AI and machine learning can serve that purpose, but maybe not in the research space I'm in, maybe in the lower length scales where there's more research in the materials and thermodynamics. I think absolutely there's scope for some of these frontiers to drive the thermodynamics and material selection choices for advanced battery, and certainly tackling the SCI growth and how can it be limited, extending life and efficiencies. So I think that's where some of the more interesting AI frontiers can have its breakthroughs. But the way I see it is the more devices at system levels, it's improving accuracies with sort of limited data and bringing in knowledge that we already know of it is the way I see these tools giving us insight within quotes.
So Shuang, do you have any thoughts from your side?
No, I just next question, maybe I can provide some information.
Okay, so I think we just have our last question to close this panel discussion. So the next question is quite general. So we have seen lots of applications of techniques such as CNN, LSTM, GP, which are now very popular. So what do the panel think are the latest and most exciting new techniques yet to be leveraged? Maybe we'll start from Shuang and Dhammika and Zhiguo.
I think Professor Chu can first.
So let me think. You first give some time to think how to answer the question. Okay. So Zhai, Huizhi, please to speak slowly. I didn't catch your question. Sorry. Yeah.
Sorry. So now we have different techniques such as CNN, LTSM, GP, and which are now very popular. So what do the panel member think are the latest and most exciting new techniques yet to be leveraged?
Okay. So yeah, so a lot of methods have been proposed. So I think to the best way important to we can combine the CNN. This is the one side to be based on the training data to get performance. And I think further we can combine the CNN and the optimizations algorithm together. That is, combine the CNN is GA and etc. If we combine together, we can, one side we can predict what we want, and also we can inversely to regulate or get parameters optimizations based on the what we want, and to reversely go the input parameters. I just think this can be more effective for engineering designs. So this is my understanding. Yeah, thank you.
So Dhammika.
Sure. The way I say it is that, yeah, AI and machine learning is a very active area, and there's very interesting research happening there. You know, there's so many interesting ideas that's been developed and been put forward. The way I see it, however, is that not all of them are relevant for the battery engineering space. You know, it's because most of might be for other applications. And based on that, the way I see it is that the challenge I'm seeing in this battery space is the dynamics, right? So that's where the physics come in. So we're trying to capture the dynamics very well and bring in data as well using LSTM, neural nets, or whatever to accommodate as an alternative approach for some modeling. Now, some of the latest, I think, areas is this, what I briefly alluded to, is called multitask latent force models. So it's combining GPs with dynamics. It's fairly new. I think it was 2009, if I'm not mistaken. So, you know, still 11 years is when some of the first papers came out from that. But I think I'm quite excited by that development and its usage. So it says combination of GPs with dynamical systems, and I think that's an interesting space to keep an eye out and see how that can be used with the technologies that we're working with. Yeah. So multitask LFM is, in my view, an interesting area.
So thanks, Dhammika. Shuang, any thoughts from you?
No, sorry, Huizhi and the others, because I'm a new learning for this machine learning. To be honest, I'm for building some experience. So but today I want to share, as what you mentioned, I want to share the data in the area. I want to grow up with our colleges to make it more valuable. That's what I can contribute.
Thank you very much, Shuang. So we can see there are lots of research opportunities in future in this area. Yeah. So now this comes to the end of the session today. So tomorrow we will have Jing Xuan as a chair, and we will have more speakers to join us to share their thoughts on AI and energy systems. And we will also announce the best presentation prizes for this conference. So do remember to join back by clicking our session link. And thank you very much again to our speakers today for the great talks and the insightful discussion. I really enjoy it. And thanks to everyone for all your contributions and support. So thank you very much.
Thank you. And maybe you can see each other face to face next year.
Yeah, hopefully. Bye.
Bye-bye.